Good evening. Hello, Paper. Hope everyone's doing well. Killer Pear, hello. Good evening. Cold there, I hear. Is it still super cold there in Northern California? Yeah, that's what I've heard. Although I tend to enjoy the change in the seasons. If you're in my other classes, you've heard me talk about that a little bit. Okay, so good evening. Welcome. Thanks for being here. Tyler, good evening. Hope you're all doing well. So we're getting down to the short end of the semester. I need to fix the display. Okay, there it is. I need to get that bit on there. Um, yeah, so I agree. It is nice to experience the change in the seasons and have the cold weather come in. Although I understand it's quite cold for you guys, so probably it'll like return to something that feels like fall sooner than later. Okay, so welcome. We are in week 12. So the big thing coming up here, of course, is that the third individual project is due at the end of week 13. So we're going to do a little bit of work just like we did last week. So last week we talked about how we get the commands from the file into the program, and hopefully that made sense. If you haven't watched that video and you're watching this video, we started on the commands part of individual project 3 last week. So this week I will finish with doing some setup for individual project 3. Before we do that though, we'll walk through the module and then talk a little bit about the concept and then look at how to solve it in the lab and then look at how to apply it on the project. So all this stuff is usable in all the places that it will be important to you, the lab and individual project 3. Okay, so our goal for the week is to take lab 11 and turn it into a template. And we'll talk about what a template is. You actually have experience with the template because you've used vectors in this class, and vectors are templates that are included in the standard libraries. So what you are doing this week in lab is you are making your own template, hand coding one, and then on the third project you'll also have a template that you create. So there's not really any new algorithms to implement. It's all the same code from last week, just reorganized as a template. And I'll remind you, as always, there's supplemental videos which are got huge amounts of spoilers in them. So if you don't like the spoilers, you can wait until after you've had a shot at the lab. Probably these videos, I don't remember for certain, but they probably have also some additional content about your upcoming project. So hopefully some of you are finding those videos that I shot back in the spring useful, but I thought, why waste the content? Come back to the lab in just a little bit after we talk about the concept, but I'm just walking through the module. Some of you have already started with const. We had a really good, by the way, you all did a really great job with your contributions to the stack and queue discussion. So the reason why I asked you about stacks and queues is because those are two additional ways that we actually take a linked list and solve problems with them. So linked lists are quite good at implementing stack and queue algorithms in programs. You'll also find, by the way, that if you look in the standard libraries, you will find that there is already a stack and a queue defined in there. So this coming week, the discussion is about the keyword const, which in C++ means a whole bunch of things, not surprisingly. So what we hope to do in our discussion this week is come up with all of the different things that const is used to do in C++. And then finally the reminders, so lab as usual, discussion as usual, and then project 3 is due just short of 2 weeks from today. So please don't lose track of that. Back to the lab. Okay, so I'm going to switch over to the REPL, and I'm going to make a new one and talk about the concept of templates at their most basic, and then we will transfer over to this week's lab and apply that knowledge to this week's lab. I'll call it templates. Okay, so we're going to make a template in here, but I'm going to point out to you before we do that you've already used a template. Vectors are templates. I'll get a using directive. So you've already experienced templates in the form of vectors, and here's what that looks like. So I have 3 different vectors here, and what differentiates the 3 vectors is the kind of data that they will store. And this right here, the int in brackets, that's called a template argument. But what templates allow you to do is they allow you to create data structures and other code that is independent of the actual data type. So whoever wrote the vector class in the standard libraries, they wrote it so that the vector will allow you to store collections of any kind of data that you want. So you can make a vector of int because it's a template, or a vector of string because it's a template, or a vector of bool because it's a template, or a vector basically of anything that exists or that you create that's a data type, you can make a vector of. So this part is the template argument, and that's how you attach a specific data type to a specific instance. Some languages call these generics, by the way. I'm going to put that in my notes on the side. Which I actually think is a helpful way to think of it. In C++, they call them templates, but in many other languages, they call these things generics. So you can pick whichever term you like better. But the idea is that this vector doesn't care what is being stored in it. The actual data type in the collection has been templated or genericized, if you will. So that's your experience with them. Now let's make one and see what they look like in code. So you can turn anything with a data type, basically, you can turn into a template. Let's start with a struct and a box. And I will have inside of it string contents. So this is going to be a very simple example. I just want to show you what this looks like. So that's great that we have a struct that has contents in it. The problem with this box is that the only kind of data it can take is strings. So if I declare a box, I'm getting a box with strings in it. And if I declare another one, I'm also getting a box with strings. So C++ has the ability to genericize or template out the specific contents of a structure. The way you do that is you use the template keyword, and then you have the template argument, and I usually say class T. Sometimes you'll see type name. They're interchangeable. I like class because it's quicker to type. Okay, so what I'm saying here with this template right above the struct is that you should find in here reference to a generic data type or a template data type called T. And I can take that T and replace the specific string with the T. That's traditional, by the way. You can call this void shoes if you want to. It's just no one does that. So what you label your template type as is totally up to you, but most people you'll see call it T for the templated type. So what I'm saying here is the struct box has contents of a type that must be specified when you create the instance. So when I create a box, I now have to provide the type of data that I want to go in that box. And to do that, now that it's a template, every time you create a box, you have to say what do you want inside of that box. So I could make a box of bool. I can make the box of unsigned int if I want. And what happens to bool with B1 is that bool is the T for B1. So B1 has a contents of bool for T. Box B2 has a T of unsigned integer, which means that B2's contents is unsigned integer. That's the most basic way to sort of explain how a template works. Now you can also, like I can make a constructor here, let's just for the fun of it, do it. And here again, now that my box is a template, where I would have referenced a data type for the contents, I now need to be careful that I'm referencing actually the templated T, which is just the placeholder for whatever the data type is when the programmer specifies the data type. And then I can say this contents equals contents, and now I can initialize these things with appropriate data. And the C++ compiler, knowing that B2 is an unsigned integer box, will make sure that the data types match when the program starts to run. Here B1 is a bool, so the C++ compiler will make sure that the data types work. And that's mostly it for templates. They're not that big a deal, really, to implement. I am going to show you, though, if I were to take this constructor and implement it separately, so once I'm outside of the class doing an implementation, the meaning of T has been lost. So I actually have to repeat the template argument here so that the C++ compiler understands that T is meant to represent some templated type. Now at that point it can make the correct, it can figure out where the data types are supposed to match. But now if I add another one, let's just say let's do a I just want you to see where these can start to get a little bit ugly. So if I were to implement this outside, so I have void box same thing. The compiler will not let you get away with this because it doesn't know what T means anymore, so you have to remind it. So these things can get pretty messy pretty quickly, and I will show you the way that I address this problem. But don't be surprised if you're reading people's code in the world that you see templated code that just becomes just a big nasty mess of template statements all over the place. If you were to look in the code for the vector class in the standard C++ libraries, you'd find this kind of stuff in there. So that's our goal, is to take our singly linked list and turn it into a template, and I'll explain what the advantage is of that once we get there. So that's the basics of a template. Templates, which some languages call generics, allow you to take a structure and remove the specific data type from it, which makes the structure usable in a lot more different places. Because now I can take a box and I can create it to contain any kind of contents that I want to, not something that's been hard-coded into it. Okay, so that's the basics. Now we're going to move on to looking at how do we use this idea for Lab 12, which is really just taking Lab 11 and turning it into a template. So I'm going to do it the the long, painful way, and then I'll show you the sort of nice, clean, and you don't have to feel guilty about it way to do it. I'm also going to show you my trick. So I have my Lab 11 from last week, which probably isn't totally complete, but I have a lot of the singularly linked list code in there. But you can save yourself some trouble here. So if I go to my REPLs link here, and I find Lab 11, if I go to the little 3 dots on the right, one of the options is fork. And if I do that, I can make a copy of Lab 11, and then I can save myself a lot of extra typing time. So that's what I'm going to do. I'm going to fork my Lab 11. So it's made a copy of my Lab 11 as a brand new REPL. I'm going to change the name. So it just did Lab 11-1. I'm going to change that to Lab 12 because that's what this is about to become. And then I'm going to, I'm going to do a little bit of cleanup. So all I really want is main, so I don't need the inputs right now. I'm not going to mess with that. So I'm going to get rid of that file. I'm going to get rid of my notes from last week. And then I'm going to scrub out main for now. And come back to that later. Okay. Okay, so our challenge this week is to take our singularly linked list and turn it into a template. So this is going to require a few steps. The first step, though, and this is because some compilers handle template code funny, and it just has, it's a matter of how templates are compiled and how they're executed. But your life is a lot easier if you put all of the code in one file. So I'm going to start by taking slist.cpp from Lab 11. I'm going to grab all of it, I'm going to cut it, and I'm going to move it into slist.h. So when I'm done, I have the original header part of slist.h. And then below that, I don't need this include anymore because I'm in the file already. Below that, I have all of the implementation code from last week. Okay, so because that's true, I don't need slist.cpp anymore. So this is what I strongly recommend. And I should just, in fact, I did require it, so that was smart of me to do that. For this lab, you are required to do it this way. So, but you'll find with templates that this is a much less painful way to do this. Okay, so everything is in slist.h. Now, a standard practice, when you have a header file that includes not just the header, but also the code for the implementation, when all of that is in one file, you'll find that people often name those with the HPP extension. So HPP normally means that you're looking at a file that has the headers and implementation all in one place. If you've used my CN reader code, that's what it does. So this, everything in one place makes template implementation a lot easier to manage, which to me is the main way I recommend you use it. When you get more experience, you may find that distributing your code all in a single file is helpful to people who are using your code. But worry more now about the fact that putting the headers and the implementation all in one file makes the templating work a lot easier to manage. So .hpp, if you see that, that probably means that you are looking at a file that has everything in one place. Okay, so now let's start the process of turning this into a template. So here's the challenges. where in this singly linked list is the component that is tying it down to one data type. So where in the singly linked list do we want to genericize the thing so that we can store whatever we want to in it? What's another way to ask that question? Somewhere in the singly linked list is a thing in which the data is placed, and it's that thing that contains the data that we want to genericize or turn into a template. Good one, Shugam. So it's this struct right here, and its constructor, which is totally brilliant. So that's exactly right. This struct for node, the node contains the data, and right now the node can only contain integers. And that's also reflected in the constructor, where we assume that to build a node we need an integer because that's the only kind of data they can contain. So if we want our singly linked list to be usable for any kind of data that we want, we have to get rid of that hard-coded integer and turn it into a template. So the way we're going to do that is we're actually going to template the entire slist class. So even though it's strictly speaking just the node itself, it's a lot easier if you make the entire slist class be a template. Okay, that's step one. I used T. You don't have to use the label T. It's what you'll see very commonly used for the placeholder for the generic type. So now I need to take that T, and everywhere in here where the node's data type is being used, we need to get rid of that. So we'll start with the node. So we don't want nodes to contain integers anymore. We want them to contain whatever type a programmer might want. Now, because that underlying value is now templated, this value in the constructor also has to be templated. There's actually two other places. We'll go hunt them down, but those are the most important ones to get started. Okay, so we've got the node. Now we need to go scrub the code for any references to integer that has something to do with the data going into the node or coming out of the node. So I have it on my screen here. There are two of them. There's two functions in here that assume that nodes contain integers. So we need to template those two functions. We need to get rid of the assumption that the nodes contain integers and replace that with the nodes containing a generic or templated type. Does anyone see those? Push front, that's a good one. Push front is correct because when we push front, we take a value and put it in a node. So we need to make sure that the value going in the node is not an integer but the generic type. Front is the other one. So front returns the data from a node, which now we can't assume is an integer, so we will change it to the templated type. So the data going into a node needs to be templated. The data coming out of a node needs to be templated. It's good to notice that there's an integer here, but this one's different because it's not referring to an integer that's inside the node. It's simply a counter that the singly linked list maintains about the number of nodes. So that one stays as an integer because the size of the list will always just be an unsigned integer. But it's important to stop on all those things and make sure you clean them up as needed. So here's the size variable. Stays an unsigned integer because it's a counter, and that will never be anything other than an unsigned integer. Okay, so now the headers are all cleaned up. Now let's go get the functions, and don't race off and do a bunch of these because I'm going to show you how I do this. But technically we have to go template every one of these functions. And if you prefer this style, then you're more than welcome to do it. Here's push front, so let's be careful. The value we're pushing is a T. Pop front doesn't do anything with the value. Front returns a T because we don't actually know what necessarily is in the node anymore. Get size, we'll template it, but it doesn't really need it. Empty, clear, to string. Okay, so those are all templated, which they need to be if this is going to work. So this is one approach to it. I'm going to show you my approach, which I just find easier to read. But this is one way to do it, and now we have a complete templated singly linked list. If we were to go in main now, we would include the slist.hpp, because that's the name of the file now. And when we declare slists, we now have to say what kind of things they contain. So we can make one with integers in it, and we'll call that the iList. We can make one with floats in it if we wanted to. So now that it's templated, we can use that singly linked list code, but we're not just limited to making lists of integers anymore. We can make lists of anything that we want, which is brilliant. I'm going to press run just to make sure it compiles. I disagree. I don't know what I did wrong. Space or enumeration. What? Oh, yeah. So, yuck. So this is actually good that you're seeing this. So I want to show you why I don't do it this way. We actually also have to, I forget which side it goes on because I don't do it this way. Let's see if that's the side. No, that's not the side. It goes on the other side. Goes on that side, I think. So I'm on line 73 here. So I have to actually have to take that T and pass it through. Yeah, so that one worked. And then I would have to do this all the way down. Everywhere where I'm doing the scope resolution, I have to do this T. I'm going to get an error somewhere else, by the way. Yes, yeah, you're right, Damien. This is very annoying. It's just a nasty old mess. Thankfully, there's a way to do it. Okay, so that's a nasty old mess, and I don't like it. And you notice I completely forgot that step where every reference to the class I had to pass the template argument through. So let me show you how I actually do this. I'm going to take all that code. I'm going to make a new file. And I'm going to put it in old and then show you how I actually do it, which I think I personally find a lot easier to read. So this is perfectly acceptable when you're doing templates to do what I'm about to do. So the way to save yourself this huge mess down here is to move all the implementation. So I'm literally going to take like this constructor. I'm going to take the constructor implementation. Notice I highlighted just the block. And I'm actually going to put it inside the header section, which it didn't respect my my tabs. Although one of these, I thought there was a formatting thing. Anyway, so one way to save yourself huge amounts of headache with templates, and I'm going to encourage that you do this in my class, with the template is you put the entire implementations inside of the class header itself, and then you don't have to have all that dang mess down there. So that constructor just goes. And you can do that for all of them. So I'm going to take the destructor and I'm going to do that with it. And I'm just going to move all of the implementations into the header file, the header section. And then I won't have any of this crap at the bottom. I'm going to start cutting actually so I remember where I was. So you've seen it, sort of the nasty way to do it, and this is the way I prefer to do it because it's a lot less nasty, in my opinion. This one is front. I'll get size. Empty, clear, and to string, and then I can get rid of all this junk at the bottom. Clear to string. Oh, I didn't do empty. I bet I put that in the wrong place. I did. Okay, hopefully I got these things in the right place. That one looks like it's in the right place. Into string. Okay, so all this crud at the bottom now can just go. Much better, in my opinion. So when you're doing templates, it is perfectly acceptable, at least to most people, myself, to put the entire implementation inside of the class header, which makes life a lot easier. You don't have to remember all that extra garbage. You don't have to type all that extra garbage. You don't have to read all that extra garbage. You just do the entire implementation right inside the class. For templates is an acceptable practice. So that's what I've done. I took Lab 11's implementation. I only had to do the template once above the class, and then everything else takes care of itself as long as I'm careful about putting the T's where they need to be. That's the whole thing. I'll run that to make sure that it works. So it still does work, so all good. Let's go ahead and test it just to see. So and then we'll do we'll put some floats in there. So this one takes floats. Forgot to print this one out to string. I need this include back. Okay, so it's just a quick test to see if my templated singly linked list works with integers and then separately floats, but now it should work with everything up to a point. So now there's my two lists. They have two different data types in them. Once you've specified the templated type, C++ will start to do type checking against you. So you can't, for example, say ilist.pushFront hello, because ilist, C++ now knows that ilist can only take integers. You'll get a compiler error about that. So I won't take a string. Okay, so that's the whole thing. for Lab 12. The whole thing is to convert it to a template. Just be careful that you are, like we just did, I just did the code, but be careful that you're checking to make sure that wherever the integer that's referring to the node's contents is present, that you replace that with the templated label T, which is what I used way up here at the top, T. But that can be anything that you want. You can make it whatever you want. It's just most people, you'll see them use T for that. Okay, so that's Lab 12. So sorry that I made you look through the mess, but I wanted you to see sort of the alternative to the way that I prefer to do it, which I think is a lot cleaner, and you're a lot less likely to make coding mistakes this way, in my opinion. Okay, so we need to switch gears. I'll let that land for a second, but we need to switch gears and start talking about Project 3 a little bit. So I'm actually going to close this and then clone it again. So I'm actually going to go back to my REPLs, and I'm going to clone, or fork, sorry. I'm going to fork the Lab 12 that I just did, and then start applying this to the problem of the third project. All right, hopefully the pacing is okay for everybody. Okay, so I went back to my REPLs, which you can get up here with, well, you can get this menu if you're inside of a REPL. One of the choices would be my REPLs. But if you get to your home screen, you should have a link to my REPLs, and that brings you to your list. I just made Lab 12, so I'm going to switch and fork this and begin translating it over to the third project. I'm going to change the name. Okay, but it's my stuff. I don't need this old one here because I'm not going to use it. Okay, so the new project, Project 3, does not use a singly linked list. It uses a doubly linked list. So before we start looking at code a little bit, I want to show you what the difference is and what the implications are for that. And then we'll switch back and forth a little bit. Come on, camera. Oh wait, camera. Okay, so we've been doing singly linked lists, and the whole idea of a singly linked list is that you have nodes that have single links coming off of them, and you have the list itself keeping track of the head or the first element of the list. That's a singly linked list. On the third project, we have to riff on this idea and convert all the algorithms to be a doubly linked list. And here's what a doubly linked list would look like. The nodes have, I'll make another node here just for the heck of it. The nodes are going to have links going in both directions. They're still going to have data on the inside, just like always. If you have multiple nodes, then what you're going to find connecting between them is links going in both directions. So the advantage of a doubly linked list is that you can move backward and forward in it, whereas in a singly linked list, you can only move in one direction. So the advantage of these algorithms is it gives us a more powerful data structure that lets us move back and forth. Now, the other thing about a doubly linked list is that it keeps track of both the head node and the tail node. So this will exercise your picture drawing abilities as you start to develop the algorithms for the doubly linked list. So we have to translate algorithms that were made for a structure that looks like this to a structure that looks like this. So we can do this. The list itself will keep track of the head and the tail. The nodes themselves still have contents, but they have links going in both directions. So let's go make some changes and start to build that thing. Okay, so what needs to change here if we're going to start building out project 3? Let's rename this S list to be D list, doubly linked list. So that's step number 1. If you start up the project, one thing you can do, which is how I'm going to do it, is I'm going to start with my singly linked list and I'm going to start translating all those algorithms over to a doubly linked list. If you don't like this approach, that's fine. You might want to start with a completely blank screen and then rebuild from there. I'm going to do kind of a hybrid of that, where I'm going to rebuild some things from scratch and other things where if it's a simple fix, I'm just going to do the simple fix. So let's change it to be called a D list. Let's go in here and everywhere where it's calling itself an S list, let's call it a D list. The constructor is going to have that. The destructor is going to have that. And I think those are the only 2 references. Yeah. Okay, so that's step 1. I changed the names. Just because it would be weird to me to have a doubly linked list that has a name that makes it look like maybe it's a singly linked list. Okay, now the next step is all those links and pointers and stuff. So the node itself still has a pointer to next, but it's also now going to have a pointer to the previous node. So that's how we make a node for a doubly linked list, is we give it links going in both directions. The previous node, one going that direction, and the next node, one going that direction. It's still going to have a templated value in it. That's still ultimately its job. We need to make sure we clean up the constructor so that previous is also null. And now we have a good, clean node. Okay, so now I need to take this comment off because it's going to be more than that. So this is a watch out for this potential gotcha. So I'm already using this node to create a pointer to the head. I also need a pointer to tail, and just heads up, I'm about to do this wrong so I can explain to you what's wrong about this. So I also need a tail pointer. Now the problem is this star doesn't carry all the way across. So technically this star actually only means that head is a pointer to a node, whereas tail is just a node. So if we want tail to also be a pointer, we have to make it be a pointer. So be careful, very, very careful about that. You need the head and the tail to be pointers to nodes, and you have to declare them this way as 2 separate pointers. So that fixes the node. That also readies the list to manage links going in both directions. Those are the first steps I would take. Change the names, update the node, and then update the pointers in the list to make sure you have one for both ends of the list, the head and the tail. And now let's just start working our way down and see what's easy and what's not. The constructor. So head is null. I'll ask you guys, what do I need to add here to make this doubly linked list start out in the correct state? Tail equals null. Good one, Sugar. Tail equals null. So that's all that needs to be done here. Because the size will be 0 and the 2 pointers will be null. So that's all we have to do to the constructor for a doubly linked list. Clear. The clearing itself may have to change. We'll see. But the destructor really still just needs to make sure that the nodes are cleared out. So that one's fine. Okay, push front. This one could be a pain in our rear. So I am going to remove parts and then go draw pictures. So I know I need a node. I know I need to increase the size by 1 whenever I create a node. The question is what happens in between. So let's go draw some pictures and see what happens in between. So the tricky part about this is there's a lot more links to contend with. So when you're drawing pictures, make sure you draw them all. So when we first start a doubly linked list, we're going to have this. And when we push front, we're going to create a node. I just say for argument's sake it has the value 10 in it. So in this simple example, all we really need to do is connect the head to this node and the tail to this node, because the first one that comes in is both the head and the tail all at once. So head, tail, and let's code that. It won't be correct, but let's go ahead and code that, because that's what we would want if we have our first node coming in. So we'll say head equals this new node and tail equals this new node. That seems okay so far. Nope. Okay. But now let's see what happens if we try to add another node in here. So let's say we want to push front 20. So now it appears that we have some problems because we need to connect how many links. We have to connect this link to the current head. We have to move this head over here. And we have to connect this link back to what's now the new node. So we need to do 3 things because there are 3 pointers that have to be manipulated. This one has to be connected, this one has to be changed, and this one. In fact, I'm going to renumber them. I recommend that when you can help it, move head and tail last. So we'll connect up the nodes first before we move head or tail around. Okay, so the first step is to take the new node and make its next point at the old head. Take the old head's previous, point it to the new node, and then move head over. So switching back over. So before we do those things, let's say this is the new one. So its next is going to point at what is presently the head. So that's 20's next, pointing at 10. Then we're going to take 10's previous, pointed at 20, the new one. Then we're going to move head over. And then let's see what happens if we move tail over. Okay, so temp next equals head. So temp next equals head means temp next points at the same thing that head points at. So we make this point here, That's good. Then we take head previous. So whatever head's pointing to, that previous one points to this new temp one. This is temp. And then we say move head over to temp. Head equals temp. And then we say tail equals temp. And that's a problem because we don't want tail to move. So we don't want tail to move in this case. So then the trick is, how do we know when we should do the tail setting as opposed to when we shouldn't? And I'll give you a hint. So here's two lists. Here's another list. Okay, so this is number 1. This is number 2. One of these lists, we should make the tail point at the new node. The other of these lists, we should not move the tail because it's already marking one that will become the tail. So which one, number 1 or number 2, should we move the tail pointer to point at the new node? So if I add a node here, should I point tail at it? If I add a node here, should I point the tail at it? So which one would you say, yes, you should point the tail at that new incoming node? These are hard. I should have drawn these on the other side, because on this one, this guy's coming in from this side. Okay, so one of these lists, I should move the tail to point at the incoming node. The other of these lists, I should not move the tail to point at the incoming node. Tricky. Number 1, good one, baby doll. So number 1, when there currently isn't a tail, then this new node is going to be the tail. Whereas in number 2, I've already got a node in there, so if I add a new one, well, that old one just moves back but stays being the tail. So if we have this situation, we do want to move the tail. If we have this situation, we don't. So then the question is, how do I detect that in code? How do I detect that I have number 1 in code so that I know that's the situation where I got to do something with tail? How do I detect this? Also a hard one. There's actually 2 ways you can detect this number 1 situation. I got everybody stumped? I think, baby doll, you're thinking along the right terms. So it's a null check. So I think, baby doll, you're on the right track with thinking about the pushback thought. And then Damien says, check for nulls. So that's the way I would do it, is to check for nulls. Technically, I'll switch the view. Technically, we only have to check, really we only care if the tail is null, then we know that this node is the first one put in the list. So it's that special situation, which baby doll recognized for list number 1. If the tail is not pointing at one, well then that new node, temp, is the first node to arrive, and it will be both the head and the tail. That's the one special situation that's different. Okay, I'm going to leave you some breadcrumbs as we go. So you're going to want, for your linked list, a push back. It's going to be very similar to push front, but you'll have to be thoughtful about those pointers. I recommend you draw pictures, but we have another week together, so if you have a crack at pushback and you don't get it working, you can bring it in and we can talk about it next week in lecture, but you're going to want to push back, so I'll just leave that as a breadcrumb. You're going to want that one. Pop front. So pop front's nasty. I think I have time to do pop front. Head equals null is still good, but let's look at the situation for pop front. Okay, so we already have the detection for an empty list, and that's fine. But let's see what the implications are of popping front on a doubly linked list. Usually, by the way, I find that in most cases, if I develop my algorithm for empty lists and for lists with two nodes, then I've covered most of the situations that matter. So you always want to count for an empty list, which we already are because we throw an exception. But now, let's see what it means to pop the front. This one's fairly intimidating. So let's see what it means. First, we're going to grab a pointer to this, which we were already doing, which is all of that stuff. So this pointer right here is going to have to be fixed. So we're going to give ourselves a pointer to this temp one, because that one we're about to delete, pop. But let's see what else has to happen. I need to move this head over to this one, because this one's now going to be first in line. So the first step I'm going to take is I'm going to take head and I'm going to move it over one, which is going to be head points to its own next neighbor. 2, I'll take the newly appointed head node and make sure that its previous is now pointing at null. And that will be one of the situations to handle. So let's start with that much and see what we get. Okay, so grab a pointer to head. We move head over, so that's all good. But now we need to, now that we have a newly appointed head node, we need to make sure that its previous is nulled out. I'll separate these out a little bit. Grab a pointer to the current head, then we move the actual marker over to the neighbor. Then we make sure that the neighbor in the other direction is nulled out, and then we can delete that node. Now what you should always be thinking here is, what about tail? So from experience I know where to look for this, but you need to be thinking about what about tail. And remember when I said that empty list and 2 nodes is often enough to get the job done, but not always enough to get the job done. So let's look at a single node situation. So our algorithm gets a temp. It moves head over. So head gets shifted over to null. And then we try to do head previous is null, but if you do head previous, when head is already null, that's a massive problem. It will crash. So after we've moved head, we need to make sure that we haven't accidentally nulled out head. But if we have nulled out head, there is no previous here. So we need to not do that. But if head is null, then tail should also be null, because that means that the last of the nodes is getting wiped out. So tail also needs to point at null. Okay, so if we move head and it becomes null, that triggers some behaviors. Crazy, isn't it? Okay, so here's head. So shifting head over may make it null. So if shifting head over made it become null, then one thing I need to do is also make tail null. Because if moving head over one step means that head is no longer pointing at a node, that means that you just deleted the last of the nodes. So if head became null because of that, then we know that tail should be null. Now if head becomes null, then this is a problem. So we don't want to do this step unless head is not null. So we're going to add an else here. So if head is not null, then we need to make sure that the node that head now is, its previous is null. That is some hard stuff. Takes a lot of work to draw pictures and to think it through to work out those algorithms. So the thing I would recommend is that you try to draw pictures of these algorithms. Set up different scenarios with the list. If you have to, which is how I did it, empty list, a 1-node list, a 2-node list, a 3-node list, until you develop a much stronger feel for how it works. Set yourself up 3 or 4 different scenarios and make sure that the code works against them. Alright, so there's pop front. You're going to need a pop back. Which will be similar, but it's working from the other end of the list, so that is going to take some thought. What else do we got? Front. So you're going to want to back. On a doubly linked list, that's pretty easy to do. Size doesn't change, empty doesn't change, clear doesn't need to change. You can still pop everything starting at the front. If you wanted to, you could pop everything from the back if your algorithm works, and you'd be okay to do that. To string, doesn't need to change. So we're going to need some more, and I will talk about those next week. I don't know if you have the patience to do it. We should do a test here to see that things work, which is what I'm about to do. So I'm going to test the basic functionality that we have built to see if it works. So I have push front, I have pop front, and I have front, and then size empty, clear to string all work, and I have not implemented these other routines. I think that should be mostly it. I'm probably going to get complaints for the compiler about, we'll just see. I should get a warning about that, but we'll just see. Okay, so last step. Appreciate you hanging out and being patient through this. I'm going to work with you next week on the hard ones. There's 2 more algorithms to add to our doubly linked list, because we're going to want to be able to insert in the middle of stuff and remove from in the middle of stuff. So I'm going to actually do those, do a walkthrough of those in class next week. But to finish tonight, let's write ourselves a little unit test and see if our doubly linked list works. So I'm going to cheat because I don't remember the code to put in here. So let me go grab. I need doc test and I need this stuff at the top. So the first thing I'm going to do is put the doc test stuff at the top, and then I'm going to grab the doc test code itself, which I have to get from the lab. This is how I work. So I like unit testing because before I get into a big messy application, I can run some basic tests to see if my data structure is behaving itself. By the way, doc test is one of those all-in-one files. I would have preferred it that the author of doc test used .hpp, but they didn't. But it is an all-in-one file. Okay, so now we can do some testing of our dlist. And I'll start just by an empty list, just to see if an empty one crashes or compiles or whatever. So I'm going to make myself one, dlist of integers, which I will call it the ilist, and then I'm going to write myself a couple of tests. So ilist get size should be 0. ilist.empty should be true, and ilist.toString should be nothing. If that doesn't compile, I'll make an actual string. So here I am, before I've bothered myself with all of the command and the file processing, all that stuff. I'm just going to spin up a quick test as I go to make sure that the features that I've implemented perform as expected. Dummy. dlist.hpp was the name of that file. Okay, so my 3 checks passed. I'm going to do another test case. Make myself another dlist in here. And then I'm going to put a few integers in it and see if it works. So I don't have pushback yet, but I'm giving you this setup so that you might consider testing with your pushback. Line 4 needs... Oh yeah, thank you, baby doll. Sorry, I didn't see the comment. I'd already... so thank you. It would have saved me trouble to watch my comments, so thank you. Okay, push front 10, push front 20, push front 30. Actually, I'm going to add a test up here in a second. So the thing to notice is if I'm pushing front, then it's going to be 10, and then in front of that it's going to be 20, and then ultimately in front of that it's going to be 30. So we should get a size here of 3 notes. We should find that the list is not empty, and we should find that the string form of it looks like 30, no spaces, 20, 10, like the last one. I failed one, it crashed. I'm going to have to run it. It crashed on almost immediately. I bet the destructor crashed it, because it crashed right here on line 14. So this is why we do tests. Let me run it with... So it did the one on line 11, and then it crashed entering into... So it's probably the destructor crashed on me here, so I made a mistake somewhere. clear. Did I forget the size plus plus? No. Made a new node. Next equals head. The previous equals temp. There's the problem right there. On a previously empty list, this is not going to work. So we're going to null check it. How did I know from experience in this case? Nope. So if head is not null, then it's safe to do this. Okay, so the situation was, I knew something had to be crashing, and I saw that this is a problem. I'm not sure why it would have not crashed the first time. Oh, because the first one I didn't put anything in it, that's why. So if you notice, the difference in the two tests was that I actually used push front in this test, and I discovered it was crashing immediately. So I went to check, and had I drawn more careful pictures, so temp next equals head, but you can't say head previous if there is no head. So I have to make sure that there is a head before I can turn its previous towards temp. Then I can move head, then I can check tail. So I had to do this extra check, which I'm guessing probably makes it not crash anymore. Okay, so the main thing I can tell you here is that a lot of your job is to find where your algorithms are crashing and then get out there on Piazza and bring it to class and send me notes if there's things you want me to discuss, and let's root out the bugs. So there is now a debugged push front. The crash, by the way, this is the experience part that I leaned on. If your program crashes, it's because somewhere you did not check for a null pointer that you should have. What I should have done for push front is run my empty scenario thoroughly, my one node scenario thoroughly, and my two node scenario thoroughly. I've drawn pictures to see if that worked. So that's fairly important because it crashed before and now it doesn't anymore. All right, a couple more tests and then we'll quit. The other thing to note here, the only difference between the empty list and the not empty list was push front. So I ran a test on that and it crashed, so I knew it had to be push front because that's the only difference here. So if it wasn't crashing here and it was crashing here, the likely culprit was push front. Let's add a couple other tests here, because in this case, I forget what that looks like. Check throws. I'm cheating and looking at this week's with as. Check throws with as. I need one of these guys. So if I do on an empty list to front, I should get an empty list error that is a logic error. Is that right? Yeah. Sorry. On the empty list. Let's see if that works. I might get an error because I need an include. Still passing. So again, the idea here is to be patient about this, but you'll thank yourself if you ran a battery of tests. I'm going to do the same test below, but this time, front should actually give me the 30 that's on the front of the list. Which it did. Same thing. If I try to pop the empty list, I should get a logic error that contains an empty list message inside of it. If I pop this one, nothing should happen when I try to pop, but the new front should be 20. So this is totally worth it because you can pinpoint the function that causes the problem. If you just add one little test, now you're passing it. Now you go implement another function, you add a test for it, and you will never be more than one function away from the last thing that had a bug in it. So still good. I could also do things like check size here, which should be down to 2. The to string after that popping front should just be 10 and 20 and 10. So totally worth the time. It's going to feel like you're spending a lot of effort on testing and not doing the actual application, but a lot of the application is there to exercise your algorithms in a slightly different way. So if you know that they're passing your testing battery, then they're probably going to do just fine with the project as well. So it's not a requirement, but it's something you might consider doing between now at least and next Tuesday, is see how far you can get filling these holes on this D list, so that when you come in next week, we'll work on insert and remove together, and then I will improve my testing, and then you'll have your D list pretty much complete. So let me show you the holes, and then I'll shut up. Push back, which is going to be very much like push front. Pop back, which is going to be very much like pop front. Back, which is going to be very much like front. And then if you're using what I've been doing here, then your project 3, you don't have to do it this way, but I'm going to do it this way next week. I'm going to add to my tests when we get our new functions in place, and then I'm going to get rid of these, and I'm going to drop in and start implementing the driver, the thing that does the commands and the file reading. So that's my plan. Okay, I got to shut up. Thanks a whole bunch for sticking around this long if you did. If you're watching later, hope you're having a good week, and I hope that there's something of use in here for you. You now have great powers as C++ programmers, and this stuff looks scary, but it's very satisfying when it works. So thank you, Little Peeper. Thank you, Shugam. Everybody have a great week. Have a good night. Get on Piazza if you have questions. I will be here next Tuesday as we make our run up to the due date on Project 3. And I'll at least draw a few of the pieces together. Don't forget also that there are supplemental videos that go through a lot of this same content, probably in slightly different ways. So if you want sort of video reinforcement, that's available if you want it. Okay, so be good. Have a good week. See you on Tuesday next week.